Hello, it's James from XRobots.co.uk. This is part 7 of my working, walking Star Wars Gonk Droid. Last time I fitted quite a lot of electronics into this, including motor drivers, some Arduinos. I sorted out the remote control as well. So today hopefully we're actually going to get some movement out of this thing. It's probably not going to walk, but we're at least going to try and make sure I can get all of the joints working and also get some sort of stability, at least in one axis. So check out last time for more details on how I'm doing this. I'm just going to get on with it in this episode and complete the wiring and write some code. I've wired in a bunch of the missing things, so we now have a power switch and another switch that doesn't do anything. I think they look quite good there actually. They're illuminated, but I haven't bothered to wire the ground in to make them come on yet. Obviously we've got a fuse behind here for the main battery power. I've also got these wires hanging out on both sides, and these are the PWMs that go to all the motor drivers. Those wires go to the Arduino Pro Minis at the back. There's 4 wires on each one, so each one is going to run 2 motor drivers and each one will run 2 PID controllers. And as I mentioned before, those are on a serial bus from the Arduino Mega that controls everything. The Arduino Mega's also got 2 PWM pins connected, and those go to the 9th motor driver, which is right in the middle of the robot there, which deals with the front to back tilt of the robot. So that's the 9th one that's going to be controlled by the Arduino Mega. This robot's going to have dynamic stability, so it needs an inertial measurement unit, a bit like the one I had in BB-8 to keep it stable. In fact, it's the same one, which is an MPU 6050. This time I've actually connected it to its own Arduino Pro Mini. It's an I2C device, and there are several reasons for that. Mainly the code base for this thing, written by Jeff Roberg, is a quite hectic thing. That means you have to integrate your whole program into that code base pretty much, because it's driven by interrupts. So what I've in fact done is got that code in this Arduino Pro Mini, and the Pro Mini is programmed to read the IMU and output the data over serial, and that keeps my own code much more minimal and separated. It also means I can use any IMU I want, provided I link it to an Arduino Pro Mini, essentially building my own serial IMU that can output the data in the same format without modifying all the stuff to do with I2C or whatever interface it uses, and modifying my whole code base, so it makes it very modular. That IMU unit is living right down there where you can see that flickery light. So right on the stationary part of the robot that I'm trying to stabilise with the rest of it. And that flashing light is flashing every time there is some data from the IMU, which is set to 25 Hertz. So 25 times a second, and the data comes out up here onto the serial interface, this blue wire, and also goes to the 5-volt breakout. Right, so I've got the Gonk Droid on the floor here, plugged into my PC with this USB cable, so that's plugged into the Arduino Mega. I've got the remote on, which is just down here, and obviously that's got the Bluetooth interface I built last time, so the Mega's reading that data for all of the knobs, and it's also reading the IMU on the other serial interface. So if we now go over and look at the code that I've got here, we can see that basically as well as integrating the stuff we had last time, I've integrated another serial read in here, which is basically for the second serial interface. So we've got one serial read checking for data in the buffer, reading all of the values from the remote, another one reading serial 2, and that's doing a parse float, and I know that's not the most efficient way to do it, and we could send the data as binary and so on, but actually it suits me because it's human readable and I can diagnose it very easily. So that's basically looking for the serial data encapsulated by another character, and it checks that character as it did with the remote to check it's what it's expecting and the data's in the right order, and if it is, it updates the IMU X and Y variables. So I've got my Arduino Pro Mini with the IMU attached to send the character Y at the beginning and end of the data, and then we can check it's correct, and again if it's not correct we can go into an error state. So then all I'm doing is serial printing all of that remote data and the 2 IMU variables. And we've got that counter again. I've now turned this loop down to run every 20 milliseconds, which means it runs at 50 Hertz. And this counts up in increments of 2, so we should see that count variable going up every second. So if we now have a look at the diag terminal, if you like, we can see the counter on the very right hand side going up. And we can see if I grab the remote here and move the slider and press the buttons, all the 1s and 0s appear all over there. And if I grab hold of the droid and go and push it backwards and forwards, we should see that IMU data, the 2 left-hand columns, we should see those varying. So One of them is the X, which will be the one on the left there, 4 to minus 5, minus 6, and obviously if I tip it the other way, the other one goes up to 3, minus 2, 3. They don't quite sit at 0. I'm not sure if the floor's level in here or whether the IMU's off, but one way or the other I can put a bodge factor in. So all of that seems to be working. I've made a little thing to measure the front to back axis rotation, which is this. So we've got a clamp here with a nut and bolt through that will go on the shaft that runs through the waist, and obviously that's in line with the pot shaft, so as that moves it will move the pot, and then we can measure it. There's nowhere to put it in line unfortunately, but that should work pretty well. If you remember, the axle that goes through the middle there, it's actually solvent welded to the end, so it rotates all through the middle, so this rotates with the body as it rotates. So that means I can clamp my little clamp on that shaft, solvent weld the pot in the front, and that will give me the exact measurement of that angle. I've now configured a PID controller which takes that pot value, takes the slider off my remote control and drives the motor, so it acts like a servo. So I've now got this switch as my motor enable switch that brings the enable pin high on all the motor drivers. I have hard switches on here as well, and the one for the middle motor is on and the others are off. So if I switch this, and now we should find that the droid will react as I move this slider. So in fact it's facing the back towards me here, so moving the knob down will make it move backwards, and moving it forward will make it move forwards. And I've tuned that PID controller quite tight, so there's a little bit of jitter, or at least it responds quite well, and you can see the thing wobbling backwards and forwards. If I do this at the right rate, then we can see that that's actually causing it to wobble backwards and forwards. So that's what's going to actually stabilise it, but next we need to bring in the inertial measurement unit. So this is quite similar to the way I did BB-8 side-to-side motion. So what we've got at the moment is one PID controller there. We've got a set point, which is basically the angle to keep the box at. We've got an input here, which is actually measuring the angle. It tries to match those and gives me an output, and that output goes to the motor. So basically this turns us into a big servo. What we need to do is drive that servo with another PID controller in front of it. The set point there will be my slide pot from the controller. My output is going to go to the input of this one, and the input here, or the input in fact, yes, is the IMU, and that's where it's going to measure. So it's going to allow me to override the angle basically, but otherwise try and keep it stable with the IMU, solving this PID and sending the input to the servo to move it accordingly. I'm building on the code from last time, so the only additions I'm going to show you are the addition of the PID library from Arduino Playground. I've also declared 2 lots of variables for my PID controllers with P, I and D values. You'll notice that the first one for the servo's got a very low I and a little bit of D, and the second one for stability's got quite a high I, and that basically makes it accelerate towards its target, and that's what you need in balancing robots. Otherwise there's quite a bit of gain. It works crudely, but it probably needs tuning as we put this thing in motion. I've also got in my setup the other bits of the PID setup there, so we've got a sample time of 20 milliseconds and limits of plus minus 255. So further down the code now, we've got the actual PID stuff, which is basically this lot here. We've got the 2 PID computes. Obviously the second one goes first because the first one is the servo, the second one is the stability that feeds it. So we've got an analog read there for the actual waste pot, and I've mapped that to be the same order as everything else at plus minus 255. I've rescaled my slide pot, and I haven't done that with map because map only deals with integers and doesn't give you any decimal places, and if you use map then I only want to move it or get a value that's basically plus minus 20, so it doesn't become very granular. So I've used cast there to turn it to a double variable which has decimal points. Then I've used division basically to scale it and turn it the right way up so I get all the decimal points, and I can feed my PID controller with decimal places on a variable, floats or doubles or whatever, quite happily. So the input to the second one is my slide as I demonstrated on paper. The set point is the IMU, does the compute, and then the first one, the input is the actual waste pot, and the set point is the output of the second PID controller that deals with stability, and that's scaled so that it doesn't overrun the end of the track. And we compute that, and then we use that output to drive the motor in either direction based on whether you know, the value is positive or negative, it swings about 0, hence the PID limits of plus minus 255. The rest of this is to do with the error state and so on for the serial data and all the stuff up here. Check out the last episode for more information on that. Right, that's all coded up, so now if I switch on my switch again, whoops, there we go. It's a bit alive now, it's a bit like a creature. Obviously my slide pot here still moves this around, and that's all fine. But if I put this roughly in the middle, let's just position that and give it a shove, it should react and try and stabilise itself, which it doesn't do a terrible job of. This is the back facing me, so it's probably going to need to lean forward slightly more. There is slightly more mass on the back, even though I've got the battery on the front, and possibly because the pivot point is slightly forward as well, so I might need to move the batteries around to stabilise that up. It has a tendency to tip back more than forward. But obviously if I push this around, it tries to kill the wobble by moving the body. So to demonstrate that, if I turn off the motor enable switch and give this a shove, we can see that it will just tip around, and obviously if it builds up motion while it's walking, it's going to start rocking. And if I give it a push and turn that on, it should kill itself and try to kill the wobble, which I think works okay. Much better than with it off anyway. And as I say, I'll need to tune up these parameters to make sure that works properly in motion while it's walking. I've now programmed the Pro Minis, which are each going to control 2 joints. So those are each going to receive data encapsulated with an identifier character, and obviously if it's not the right character it won't do anything, but it will still read the data and clear the serial buffer. So they're all on a common serial bus, which will eventually be connected to the Arduino Pro Mini. So this one I'm looking at is C, so it's got a variable called I am, and the value in there is a character of C. The others are of course A, B and D. So I've got some offsets here for the joints because the pots aren't all straight. They're mostly in the middle, but we can fine tune the 0 positions, and the positions centre around 0 with a swing of plus minus 255. So I've got my 2 PIDs being set up there with some various values in. I can fine tune those as I go. Some various variables there for reading the serial stream, updating it to the joint positions, the demand positions, and the actual joint positions that get read in from the pots. So again, that's the PID declaration, so we're running at 100 times a second for these, and if the time is right, so for more than 10 milliseconds since the last loop, it runs the loop, reads in the serial data, so it reads the ident and ident2 with the 2 positions for the demand positions in the middle. Obviously it only updates if those idents match what it's expecting, and if that's the case it updates the joint demand positions. It then reads in the pots and scales those so those are the same sort of order, plus minus 255. I'm also scaling the, or rather constraining the joint position so I can't make the legs fold in half. So I've set that to plus minus 30 in this particular case. It's different for the side-to-side joints, for the knee joints and so on. We then run both PIDs and turn the motor as before in either direction based on a value. I've got a dead spot there which I might increase or decrease depending on how I tune those PID controllers, and that's all it does. Right, so we're just going to test that out on controller B, which is this pair, and that does the 2 joints on the side of the leg here. So I'm just going to turn on the motor enable. I've obviously got my enable on the remote as well, so I can turn that on and off if I want to, but they both need to be on for it to work. The other motor enables are off for now, but if I just go onto my serial terminal here and type in something, give it a position of 10 for now, so we've got B, 10, 10B, and if I hit enter, you should see that leg bend a little bit. I can be a bit more venturous with that. Obviously I don't want to tip it over because the sideways joints aren't working and there's no stability and the other leg's not turned on, but if I do 30, then we can see that it bends to 30. And this particular one I've constrained to 100 because 30 isn't much, so let's go a bit further. That's 45, there we go, and if I go back to 0 again, should take the leg straight again. It seems strong enough to push it up, which is good. The next stage, as you might expect, is to have the Arduino Mega send the commands to the Pro Minis and basically do that in a coordinated fashion, reading the IMU, keeping it stable to do all of the actions walking along. And of course the remote will send commands to the Mega to say when I press this button, now trigger the sequence for walking along, and it will make a number of steps, whatever I decide gets programmed into that button, and similarly for the others for turning once that leg splitting mechanism is done. I've also got other buttons that could be like crouch down, or it could be stand on one leg and wiggle the other leg, whatever it is, but all the control will be done by the Mega instead of me typing the commands in. So basically I've taken the last serial out on the Mega, the TX3, and I've wired that into all the RXs on these Pro Minis. Now, if you do that sort of thing, you can't actually then program the Pro Mini anymore because it gets confused. The serial is active high, so basically it means that it holds all these pins high, and then the programming doesn't work anymore because it's using the same serial interface. So I've got a little switch on the top just hidden behind that basically takes all those 4 wires. They're on a 4-way toggle, a 4-pole toggle I should say, and when it's back it's disconnected and all those wires are completely disconnected, and when it's forward it's connected to the Mega. So I can still program the Pro Minis to adjust the PID controllers without disconnecting the wires. I've written some really simple code to bend the legs when I press buttons. So I'm looking at button 8 on the controller and button 7 for the left and right legs. So this block of code here deals with the left leg, and the similar block below deals with the right leg. And all it does is waits for the button to be pressed. It waits for a thing called left flag to be 0, which is 0 to start with. Sends to controller B, so that's the data encapsulated, sends those 2 positions of 50, sets left flag back to 1, and resets the clock. So basically it's multitasking, so they can both run simultaneously. And then the next statement is if the left flag is 1, as it's been set already, and the time has expired, which is half a second in this case, then set those positions back to 0, set the flag back to 0, and then it can wait for the button press again. So it's sort of manual. I press the button, it bends the leg and straightens it half a second later. The right leg does exactly the same thing with a different button, so I can almost try and sort of hit the buttons in turn and make the legs bend, and we can test how strong it is mechanically and whether it looks like it's going to work. Alright, so I've now got my buttons programmed on this remote, as I say, that bends each leg in turn. So if we just turn on the motor enable, I've just programmed the buttons on the right hand side here. So if I press one button, it bends one leg and straight back after half a second, and if I press the other one, should be the other leg. You can see it almost taking a step there. So if I press both of them at once, obviously it crouches down and comes back again. And if I'm careful, I can almost get it to take steps. So the main thing was making sure that the legs were mechanically strong enough that they'll actually support the weight. So if I bend these kind of in turn, oh, yeah, we can see that in fact one leg is strong enough to push up and lift its whole weight up on one side. So at the moment this is obviously manual timing. And we can almost see that obviously the thing looks like it's going to walk, which is pretty good. So the next plan will be that we'd automatically have a button where we press it and then it automatically takes the steps, so I don't have to go and press the buttons to do it manually, and then we use the inertial measurement unit to keep it stable so it doesn't build up momentum and overbalance. And there's 3 ways we can do that. One of course is to read that IMU side to side as we did back to front and have that alter the hip positions and the ankle positions, so it tries to keep its hips above it, and then that should keep it stable and stop it going, well, hey. We can also alter the timing between steps, of course, so if it seems to overbalance, it can wait a bit before taking the other step back, and that can bring it back on balance, again reading the IMU. The other one, of course, is we can go and take a wider step out to bring itself back on balance. So using all 3 of those together, we should be able to make it basically stand there, pumping each leg and staying perfectly stable in the middle and almost perfectly level. And it looks like, as I say, the mechanical design is strong enough that each leg can actually push it back on. So that's pretty good, and I'm glad those motors are the right speed and the right torque rating. They all seem perfectly happily powered from those motor drivers. But you're going to have to wait for next time to see that, so don't forget to subscribe for more updates on this project and lots of other projects, and also check out my Patreon campaign at patreon.com/XRobots if you'd like to become an XRobots superfan, and you can get access to an exclusive live broadcast with me and also all my main build videos uploaded early. Alright, that's all for now.